All right, thank you very much for joining everyone today. Appreciate you taking the time out to join the November edition of the Liftoff webinar series, put on and sponsored in part by Lyft, as well as the Michigan Manufacturing Technology Center. Today we are featuring Munro and Associates. They're going to talk a little bit about their lightweight battery trays for electric vehicles technology. So thank you very much for joining. This is Joe Steele at Lyft headquarters in Detroit. Have a couple of housekeeping issues to go through before we get rolling with the webinar. Please, again, put your phones on mute as we can eliminate as much background noise as possible. Would make it a much better presentation. Second of all, if you do have questions, please use the chat function that's on the GoToMeeting taskbar. It's on the right-hand side of my screen. You can address that question to the organizer, and I will help facilitate the Q&A at the end of the presentation. Thirdly, each of our webinars will be recorded and is posted on the Lyft website for future viewing or sharing with the friends and family who were unable to make it today. So please go and take a look under the technology tab of all the Liftoff webinars that we've had in the past, and you can see as we get them scheduled going forward in the future. We are here on the third Thursday of each month. We do take the month of December off, so we won't have another one of these scheduled until January. But stay tuned to our website and stay tuned to your emails for upcoming speakers as we roll around to 2019. A couple things in case you didn't know about Lyft. We are Lightweight Innovations for Tomorrow. We are part of the Manufacturing USA Network, which is a network of 14 national innovation institutes. All of us have different technology focuses. Lyft happens to be lightweight metals, so our goal really is to revolutionize lightweight metals manufacturing through innovation and education. We do that three different ways. The first is technology development, part of which you're going to hear today through our membership. We are a membership-based organization, and we have a number of innovation development R&D projects going on across the country. So you're going to hear some of that today. We also focus on technology transitions. We believe that there's no use in developing this new technology if we don't help transition into the marketplace. So we certainly work on that. And finally, education workforce development. Again, if you develop this technology, transition to the marketplace, we want to make sure that the workforce has the knowledge, skills, and abilities to utilize the new technology when it does indeed get into the marketplace. You can learn more about a number of our projects as well as our education workforce development initiatives on our website at lift.technology. As I mentioned, we are based here in Detroit, so please come on by and visit if you are in town. We do share space in our lab with IACME, which is another of the Manufacturing USA Institutes. They focus on composite materials, so we have lightweight metals and composites in the same place. You can also follow us on our social media channels at News from Lyft to tell the world about the good things you heard today that Munro and Associates is talking about, and you can tell the world when you come visit us here in Detroit. A few highlights from the lab I mentioned, our lightweight innovation facility that we share with IACME here in Detroit. You can see on your screen a number of the large-scale pieces of equipment that we have ready for your use. So please give us a call if you have ideas for lightweighting projects you're interested in, a problem that you have that you're looking to solve. Please contact us at lift.technology. Come visit us, and we'd be more than happy to work with you through those problems with our in-house engineers or any of our network experts. I will highlight the linear friction welding machine that you see on the equipment list. That is in the process of being installed. We are thrilled to have that piece of machinery. We just took possession of it last month, so it is being installed now. It is the largest linear friction welder available in the country. If you wanted to do the kind of work that you would be able to do with this machine, you'd have to fly across the pond over to Europe somewhere. But we are very proud to have that machine here in Detroit. As I mentioned, these Liftoff webinars are brought to you by Lyft, as well as the Michigan Manufacturing Technology Center. And on the line, I believe I have Elliot Forsyth from the center to share a little bit about what they do and how they can help manufacturers as well. Elliot?
Joe, thanks. Can you hear me okay? Joe, can you hear me? Great, thank you. Well, and thanks for the introduction. And you know, we're pleased to say that we've been a partner with Lyft since its beginning nearly 5 years ago. And our role in this relationship is we are the connection point, particularly to small to mid-sized manufacturers. We've been commissioned, and we're 30 years ago, to drive the continuous improvement and development and prosperity of small to mid-sized manufacturers, and we do that in a variety of ways. As you can see on the chart here, where we focus a lot on top line and bottom line growth, but we also focus on areas such as improving leaders within the organization to drive more business opportunity. And we do technology acceleration, which includes things such as Industry 4.0, protecting your data through cybersecurity, and our strong collaboration with Lyft. Next slide, please.
I think that's all we have right now.
That's all we have. Well, I'll just add a couple other points. We are part of the National Institute of Standards and Technology, which means that there is one of us in every state with the same mission and goal. So what you would find, as Joe pointed out earlier, there are a total of 14 USA Innovation Institutes across the United States, and an MEP is that connection point to the small to mid-sized manufacturers. So thank you, and enjoy this very important, timely topic. And I'll turn it over back to you, Joe.
Thank you very much, Elliot. So enough about Lyft and the Michigan Manufacturing Technology Center. At this point, I'm going to turn the presentation over to Ron Gillingham with Munro and Associates to talk us through his work on lightweight battery trays for electric vehicles. So, Ron, the presentation is yours.
Thank you very much, Joe. Can everyone hear me?
I think we can.
Okay, very good. I want to thank the folks at Lyft, Joe, and the folks at the Michigan Manufacturing Institute as well. We are in Auburn Hills here. If you walk outside of our building, you can see the Chrysler Tech Center. So easy to find us here. And we have been an engineering services provider for 30 years. Just a couple words about Munro. Our founder, Sandy Munro, used to work with William Deming, and it was Deming who suggested Sandy should be a consultant and, as they say, go for the big bucks on the outside. That was while they were both working together at Ford Motor Company. So 30 years ago, Sandy started this company, and since that time, he has established and cultivated his global reputation for excellence. We have now approximately 80 team members in Munro and Associates, and our expertise is broad and covers a number of industries. Today, we're going to be talking about some automotive technologies and associated componentry to electric vehicles. A very hot subject today, and we're doing a lot of work for a wide variety of folks who are trying to support and get into the EV field, materials, manufacturers, even investment institutions. You will see companies like UBS, Deutsche Bank, all of these large investment companies are now interested in the transitional phase of the transportation industry. You will hear folks referring to us now as the mobility industry, and Munro is right in the center of that. I just referred to one of Sandy's charming sayings. the boss says, we have worked on everything from the Barbie doll to the space shuttle. And we have, in fact, done that. So we're not only automotive, we do aerospace, we do marine, we do medical products. We are into technology transfers, just as our friends at Lyft. And we are commonly coming on board at the point where folks want to see these things commercialized. And so we do a lot of cost estimating. We're famous for our benchmarking, but we are not a requisite supply house. If you need to check off a box that says you benchmark something, you know, you can get a bunch of high school kids to tear that apart for you, and okay, you've done benchmarking. But we do detailed analysis here, recording many attributes that factor into the cost models that we present. Our cost models are famous for their accuracy. We have government agencies coming to us for that reason: California Air Resource Board, National Highway Transportation Safety Administration. All of these agencies are coming to us because of the accuracy of our numbers. So just a couple frames here dedicated to what we do here. Sandy put this chart together about 30 years ago, and you'll see folks use this over and over again. It's something important for us to remember in the engineering world. When you look at the distribution of a project's funding, you can see in the lower left-hand corner that most product design efforts only devote 5% of their overall budget to product design. But if you go to the upper left-hand corner, you can see that at the design level, once you start putting lines into a computer, you have determined 70% of the cost of that product as it's manufactured. And so moving over to the right, you can see in your budget, you may have 5% for product design, 50% material, 15% for labor, and 30% for overhead. And what this means is that all the way out on the right-hand side where you're manufacturing and you're dealing with overhead, yeah, we're all familiar with VAVE programs, but if you look up, you can see a VAVE effort, once you're in manufacturing production, is only going to have perhaps a 5% impact on the total cost of that product. And if you can bring home a 5% cost save, a lot of folks are really excited about that. But what this chart says is that you, as an engineer and a professional in this industry, should be devoting more attention to the left-hand side of the world. That would be your product design, and you should be bringing in manufacturing, materials, purchasing, and everyone driving towards a common goal that is going to make the company more profitable. So in the past, yeah, you've seen these BASF commercials. They don't make the product, they make it better. Well, we don't make anything here at Munro and Associates, but what we do is we bring value, quality, and profitability to the customers that we collaborate with. We do that through lean design. In fact, lean design is a registered trademark of Munro and Associates, so that's how long we've been at it. And it's important, especially these days, where companies are measured by their stock performance, not just the profitability of the company, but profitability drives stock value. And we have a number of examples. If you folks have time to look at some of my LinkedIn articles, you'll see there's a correlation between lean design, profitability, and shareholder value. So let's get on with the presentation. We're talking a little bit about battery trays, their functions. Yeah, we call it a battery tray. It's a storage cell retention system. Yeah. So today we're going to have 3 vehicles with little snapshots in time, which reveal some of the details and choices made when considering energy storage in the context of electric vehicle architecture. The 3 subject vehicles that I'm touching upon today are the BMW i3, Chevy Bolt, and most recently we did work on the Tesla Model 3. Off on the right, you see I'm talking here about what the annual volumes are, and this is very important when you start to calculate the profitability of a product. Obviously, you want to match your manufacturing methodology to the volume that you're ultimately going to sell that vehicle in. And just another word now, BMW has hit 35,000. That was their peak number for the BMW i3. Chevy Bolt is approaching 30,000 annually now, and I would expect to see that number growing, but not as rapidly as Tesla Model 3. They're over 200,000 units a year now, and they're going at this from a volume perspective. They're really trying to change the marketplace, and quite frankly, there's a lot of really brilliant engineering in that product. We'll set aside the fit and finish for now. Okay, so first vehicle up by the vintage of the vehicle was the BMW i3 with the range extender. And these are just some of the vehicle specifications. When we talk about the range here, we're strictly talking about battery range, and this 150 miles. The vehicle weight, 3,000 pounds, is really rather light when you start comparing it to the Chevy Bolt and the Tesla. Tesla has a body structure which is incredibly robust, and in the opinion of many, including Sandy Munro, a bit over-engineered. So again, we're moving down this chart. Kilowatts of storage is only 22 kilowatts, and I say only 22 because both of the subsequent vehicles are going to show you that they have more kilowatt storage and therefore greater range. The body architecture of this vehicle was quite noteworthy, and that's why Mr. Munro funded the analysis of the BMW i3 himself. 90%, 95% of the work we do here at Munro and Associates is in order to fill a customer's specification and requirements, and therefore that work is all protected by non-disclosure agreements. Pardon me. What you're going to see today is all work that we have within our building done on our own and have full license to sell reports on these vehicles and work with anyone who is interested in obtaining information on these vehicles. One note about the analysis for the BMW i3, this is what we call a bottoms-up analysis. So every bolt, every screw, every stitch in a seat cover is counted, and all of those are put into a pricing model. The total report is over 54,000 pages long, and it took us a year to complete that work here at Munro. So this is just a very small section of the work that was done. We put all of our subsystems into what we describe as zones because we don't always have the manufacturer's part numbering system to work with, and zones are common, so it doesn't matter if we're looking at a Fiat, a Ford, or a Chevrolet. All of those subsystems are broken out into the same zones. We call zone 4 powertrain and driveline, the bin that we're going to be putting all of our battery, electronics, and cooling systems in. So the last line on this page here is kind of important. This battery tray is integrated with the body structure for vehicle impacts. So FMVSS 214 is something that you cannot meet without having the battery tray in place. And basically what you'll see when you analyze the structure of the vehicle is there's a big front end aluminum subframe, a big rear end aluminum subframe, and then tying those two together is the aluminum battery tray structure in between. So the materials in the battery tray for the BMW include extrusion grade aluminum and rolled aluminum plate. That's for the base of it, and then there's a thin sheet metal aluminum cover that goes on top of it just to seal out the system from the environment. The manufacturing methods used on the components in this battery tray are extrusion, stamping, and a lot of CNC machining. Integration of and packaging of the cells. Now, 3 different manufacturers have made the cells for these vehicles. BMW has Samsung prismatic pouches with a manganese, nickel, cobalt additional weight from the bricks. I'm going to talk about the bricks in just a moment. Is 10.52 kilos. And these bricks are basically the containers which protect the cells, the anodes and diodes, from any damage in the vehicle environment. So, BM battery tray is all aluminum. Because the assembly is completely done in aluminum, galvanic issues will not arise as they do in the Tesla Model 3 tray assembly. We'll talk in a moment about that. But here you can see the complete battery tray with the cover on it. In the lower right-hand corner, this brick I just referred to. The prismatic cells are arranged in this brick, and the brick is then bolted to the battery tray, the bottom of the battery tray, to keep it in place through vehicle dynamics. So talk a little bit about what is inside the brick. Upper left-hand corner, you can see the rolled prismatic pouches, okay? So there's an anode and a diode in there, and there's an electrolyte. All of that gets stuffed into the image that you see in the upper right-hand corner, and that is basically a beer can thin deep draw stamping, and that aluminum housing protects the pouches within and then provides you with a topper mount for the plate where you can see the cells are being tied together. Now, all of those little individual cans are placed. You can see them in the lower left-hand corner. There are 6 being placed here, and this is kind of a unique breakout of the battery tray because it has this end weldment taken off, and you're looking directly into that brick assembly. This is an insulator for thermal and any shifting that might occur within that brick, and there's very little movement within there, I can tell you that. And I would like to invite anybody listening in today, come on out and you can see all these physical properties on a tour of Munro. Be happy to host you myself. It costs you nothing. So talking a little bit about what that brick is made of, kind of hard to see here in the upper left-hand corner, but there's a giant strap that ties these together. This is going to be out here on the end of the brick, and internal to the brick, you can see they're flanged in opposite directions. Wire welds, lots and lots of wire welds. Here's the front plate. This is a flat stamping that has these piercings through it. And then in the upper right-hand corner, you can see what you were looking into here. This is an extrusion profile that is then subsequently machined. You can see all of this is being cut out, and then the attachments are being set up in the lower corners of that. So that's what that extrusion looks like in a side view, not an end view. You can see where they've cut through it in order to put these straps in the center, right through the assembly, and the outer plates onto the ends of it. So there's a lot of material involved here, and like I said, over 20 pounds of weight ultimately in the final assembly. So we're going to talk a little bit about what the tray, the base of this system, is composed of. There is a stamping on the bottom of the tray assembly, and that's the only stamped part aside from the lid in this whole battery assembly. Everything else is extruded, and you can see, again, lots of wire welds. This is at the front of the battery. You can see access ports here for the heating, cooling, electronics to come through. Another access port over here. A lot of fixturing is put into this. And again, as you look at these welded corners, you can see that there's a lot of grinding being done on this. It's all managed very cleanly. But what I can say about this particular assembly is that this can be done almost anywhere. You can see that the profile of the lower stamped plate is very thin, right? Okay, and because they're using all aluminum, there's no coatings on here, no galvanic reactions that they have to worry about, like on the Tesla, and I'll be showing you that in a moment. But what you see is that with this stamping and these extrusions, this can be manufactured just about anywhere in the world. Aluminum extrusions are quite common. There's nothing special at all about this base plate stamping. This is the battery tray cover, and you can see I was asked to pull in some of the cost and data here, and I wanted to do that for this part. You can see that the E-coat, $2.31, and the stamping itself is at $19.84, and I believe that's with the coating on it. So this, again, is one of the detailed breakdowns that we went through on the BMW. Every single part analyzed, and when you come out and visit, we can show you how our analysis tool, Design Profit, is used to track all of those costs and to order them in a sequence which reflects the actual assembly of the product in production. So let's get to that base plate. We'll talk a little bit about the number of parts. 54 parts, 40 fasteners, 14 individual unique part numbers, 790 process steps to put this baby together. 30 fastenings, yes. And this is kind of important here, right the first time. This is one of the methods and one of the metrics that we're used to track quality. And we can help you determine what your CPK value is for your process. And we have a methodology, again, within Design Profit that we use to determine what that number is. There's formula bars in there. And I'll just make one more reference to Design Profit here to explain a little bit about this. William Deming, everybody knows, yeah, very famous for his methods of efficiency, and made Toyota quite famous, and largely is the founder of the TPS, right, Toyota Production System. The only thing is William Deming did not have the PC that I'm working with right now. Computing power is not something that Deming had. Now, on the other hand, Sandy Munro has had the benefit of computing power. And 20 years ago, he began development of Design Profit. That is our in-house software. It's proprietary to Munro & Associates. And we believe it's the best cost estimating tool on earth, as well as one of the most powerful tools to help track manufacturing costs and help discover ways to increase the profitability of your company. So we'll go down this chart a little further. Supplier process time, you can see this is almost a 40-minute cycle time in producing this. Total weight is 18.87 kilograms. Now, having said that, you have to look out here on the right and see that there's an additional 10.5 kilograms of weight that's associated to those bricks I showed you just before this. So all of those bricks go inside here. There's an associated cost to that as well, which is separate from the cost of the tray that you see down here. Q burden is, Q burden is what we describe as the cost of quality. So this is going to involve all of the inspection points that you have in the plant, any of the scrap that you generate while manufacturing this system, and really that is not too terrible bad of a number to see in there. All of these numbers here are production numbers and do not include SG&A and profitability of a supplier. This is what you would spend if you were manufacturing it yourself, not buying it from an outsource. Okay, so underneath the battery cells, let's start up here on the upper left-hand corner. You can see those bricks in place, yeah, and then underneath it is the cooling channel. And go back one frame. You can see these reliefs stamped into the lower component of the battery tray. That is where these cooling and heating management elements are put. And I'll draw your attention to the construction of this very simple manifold. You've got these very thin ribbons which are completely open on the inside. Those lie on top of a plastic V channel, and the V channel is set up so that it maintains constant contact with the bottom of the plate. So it's almost like a plastic spring. You can see that V channel there. It's inverted now in an A shape. So on top of that plastic carrier are two elements. One is the heating element, and that goes underneath the aluminum ribbon that comes off of the manifold that they run an AC refrigerant through. So this is not a typical glycol system for managing the thermals here. This is actually AC refrigerant being run through these micro channels. This is an advantage in that there are no heating and cooling requirements aside from that AC line that have to get into the battery pack. And I'll show you a little bit more when we get to the Tesla that identifies, how complex this heating and cooling thermal management can become. So we'll talk a little bit in summary about what you can expect in terms of costs, and each one of the subsystems within this battery pack. Battery pack includes the tray, the cover, all the cells, all of the bus bars inside, all the cooling and heating elements that are required to be in that space of the vehicle. You can see manufacturing costs, and these numbers here, you can see there's that qualifier that this is excluding R&D, logistics, and a profit margin. But it does include material cost and purchase parts cost. So kind of an interesting equation here. At the end of the day, you can see that that quality burden is a pretty considerable number in respect to the overall price of that battery that you would expect to see a customer or a warranty claim bringing in. So real briefly, I'm going to jump to the Chevy Bolt, and I apologize, I don't have as much information on the Chevy Bolt as I would like to have. This was a unique type of analysis. We do 3 different types of analysis. We do what we call bottoms up, and that's what we did for the BMW. We do what we call quick cost, and that's what we did on the Chevrolet. And we did that for an investment firm that wanted to understand what this baby was made of. And really, for the money, the Chevy Bolt is quite an impressive vehicle. So this part of the vehicle, the battery tray, the cooling plate, was on tour in Europe and never came home to us here at Munro. So I'll make apologies for the limited amount of information that I have on the Chevy Bolt. Just talking a bit about what the cooling system and thermal managements are while we're on that subject. Base of the tray is steel. The cover that goes on top of this battery tray is a composite, and it has a very deep draw in the area of the rear seat of the vehicle, and that's where the management system, the electronics and battery management system for this assembly poke through the rear seat and the underbody of the vehicle, giving access for service in case any of that needs to be attended to. But here's something to consider when you look at the thermal management strategies. This is a pretty darn big stamping here. It's 2 pieces and it's welded together. These are the ports that the coolants run through, okay? In conjunction with that, there are some insulators that are used. You can see here, these insulators are sitting on top of the cooling plate. These insulators are what's shown here in green in a page out of the Chevy parts book. These on top look to be a non-woven material akin to the 3M branded Thinsulate product. They are used to handle thermals and keep the thermals inside of the battery pack and not have them move out. These lower plates that you see here in yellow, these are expanded polypropylene foam. And what they're doing is basically two functions. One, yes, they have thermal properties, and they're going to prevent road heat from coming through that steel pan and loading up your battery cells with heat from the road, reflected heat. So the EPP is an effective thermal insulator, but more importantly, it sits underneath the battery tray, underneath the battery cooling tray and the cells themselves, and it provides some impact and vibration isolation. Of course, you've probably been familiar with expanded polypropylene foam products in bumper applications. It is a great energy absorber, and therefore it seems like a natural fit in this application. Not a bad job with regard to management of the thermals here. I want to jump to the Tesla now, talk just a little bit about what the vehicle is and how it functions. This is the big winner on range, right? This is what they're selling this baby on, 310 miles of range. You can see it's significantly heavier than the BMW at 3,800 pounds, and this is the really great story here. 75 kilowatts, and that is a conservative estimate. Typically, this number is a hot bone of contention, and really it shouldn't be so important to folks. One thing that you have to understand and remember is your range is impacted more by environmental impacts than it will be by the total kilowatts. If you're in a very cold environment and you're running that heater, or a very hot environment and you're running your heating and cooling system, you're going to be killing this and killing your range as well. The body architecture, it's an aluminum steel hybrid, and really it's built like a tank. They left, I would say, some dollars on the table in not executing a very efficient body structure. Now the storage cell, these are rolled 2170 lithium ion cells that come from Panasonic, and they have some structure of their own. And this is important to understand as well. This battery tray has no impact on the overall global torsional stiffness of the vehicle. You can remove the battery tray and it only has 3% impact on the global stiffness, torsional stiffness of this vehicle. So it's really kind of a body structure that stands without the battery trays. However, in the future, I would look to see more of these battery trays integrated into the body structure and helping to provide the performance that's required for FMVSS 214, side impact primarily. Talk a little bit about what this battery tray looks like coming out of the vehicle. You can see this is the tray as it comes out. That's a full complete assembly. This is at the back of the vehicle. This comes up under the rear seat, and this is where a lot of the thermal management is. This is the cover removed here in the center, and you can see there are basically 4 logs. I'll refer to them as a log for the time being. These are molded potted structures, and they do not require a protective sleeve like the prismatic cells that are in the Samsung cells for BMW, and LG provides the cells for Bolt. They have CADs. These are rolled and basically have the same outer structure that your AA batteries will. Show a little bit more about that battery. There it is. It's called 2170. And you can see here this quote from Elon Musk. It's the highest energy density cell in the world and also the cheapest. It's 50% larger by volume than the 18650, which was in the Tesla X and Tesla S, but it could deliver almost double the current. So this is a very important development and really gives Tesla the greatest density of energy storage per pound of any other battery system on Earth currently. This shows you in the upper right-hand corner how the cells, these cells here, are tied together in a giant bus bar, and how they are terminated. Just these little fine wires, and I believe that's a laser weld on top. That shows you the tray as it came out of the vehicle. Talk a little bit about the material. It's a 6000 series material, and this battery tray, by contrast to the BMW, cannot be made just anywhere because of the depth of draw right here. Okay, and this is showing you the backside of the battery. This depth of draw is so deep and so exaggerated, and it's about, I'm going to say it's 125 millimeters, that this requires a pretty doggone big press. So this was done with a high volume product in mind. You could not afford the capital investment into the stamping tool for this battery tray were you not making 200,000 of these. So you can see a lot less parts involved in this battery tray, a lot less fasteners than the BMW. The total weight, again, you need to go back and compare both the bricks and the battery tray of the BMW, and then understand that it's, you know, 1/3 of the storage in terms of kilowatt hours that the Tesla has. So the Tesla really has tremendous density and is delivering more power per pound than any other system we have ever analyzed here at Munro and Associates. Talk a little bit about what it's made of. Again, you can see up left corner here, upper left-hand corner, this is the draw that is on the forward edge and the rearward edge of the battery tray. Due to the length of the battery tray and the weight of the cells, you can see they have incorporated into the construction a couple of extrusions. This is an extrusion here cut on an angle, and this is an extrusion I'll call a rail, okay? These are adhesively bonded in, and also they have friction stir welds right here, friction spot welds, I should say. You can see them along the rail here. And that red line, that is the adhesive underneath it. It is then bolted to this extrusion, and this extrusion here goes through the front of the battery case and bolts into this casting. It's either a casting or a forging here. I have to pull it out and do analysis on it. But this was what we call quick cost. Unlike the BMW, we did not spend a year on this analysis. We bought 2 Teslas, tore one apart, and then instrumented the second vehicle for track testing. So the analysis on this took about 4 months, contrasted to 12 months for the BMW. And this is a systems level cost, not an individual component level cost. Again, you can see this extrusion. There's 2 unique extrusions for the rails. One in the center is unique to the outboard rails. And these were, as you see them right here, that is what divides these logs that I was referring to before. Okay, so we'll jump back here, and basically around the periphery of this system, there are weldments. On the front and the rear edge, there are aluminum weldments. Those are friction spot welded into place and adhesively bonded. Note that the entire battery tray assembly is coated. It's painted to prevent galvanic reactions, and also this particular series of aluminum is not as resistant to corrosion as the material that was used in the BMW. Talk a little bit about what they're welding on here. Okay, this is a steel component. On the periphery, there are 4 of these stampings that are welded into place, and they hold the outboard edges of those logs in place and keep them from moving inside of the battery tray. On the back edge here, again, you can see this is an aluminum stamping here, and it is both friction spot welded and adhesively bonded into place. Those are the friction spot welds that you see right there. Now there is a another stamping in the front. So there's a total of 4 steel stampings, and that's why they had to coat this battery tray so that there were no galvanic reactions. I'm going to talk a little bit about thermal management in the Tesla, pardon me. Common terminations out here at the ends of these ribbons keep the cost low and make it a very repeatable system. Now, just a word about the patented Tesla cooling tube. This tube is rather unique, and unlike what you're seeing in this illustration in the lower center portion, out on the end, pardon me again, out on the end here, you see these terminations. So instead of looping, they together in this manifold shape out here on the end. Sorry about that. Okay, this shows you what they look like as they're molded into the log. This shows you a little bit of that potting material. So what they do is they assemble all of these cells, as you can see here vertically in the vehicle. They put the ribbons in between for cooling, and then they pump this full of this potting material. This green material is both a insulator for thermals, and it is an isolator for vibration. So you can see here, this is adhesive is used to attach battery cells to the cooling channels and covers the battery module. Thermally conductive adhesives minimize the vibration between the components. So it's kind of a really neat structure. It is not structural in and of itself. This potting material is soft and can be broken apart, but within the confines of the battery tray, the tray itself has enough structure where the battery cells being molded together have no structural requirement on them. Okay, talk a little bit more about comparing each one of these systems. This is powertrain and battery pack total weight. I like this illustration because it shows you the composite battery cover for the Chevy Bolt, and you can see the cost of these respective systems is pretty close. BMW has the least storage power and range of all. When you move into the Chevy Bolt, you've got twice the storage energy, at least, of the BMW, and you can see only 100 kilograms more. Really a dynamic vehicle. You get into that little Chevy Bolt, and it has an equivalent of 200 horsepower. So it really runs like a demon and sticks to the road with the extra weight of the vehicle, kind of like glue. So really a very nice execution. If you want the best EV for the smallest amount of dollars, you might take a look at that Chevy Bolt. And these are the battery packs and the respective prices and weights for those battery packs. You can see these are some pretty significant structures, and this is approaching 1,000 pounds here. So these are not lightweight. They add a whole lot to the overall weight of the vehicle. And talk about material distribution, and this is the one that really threw me as I looked at it the first time. Draw your attention to the BMW composite body shell, and everybody's thinking, well, it's a plastic car. They've avoided using a lot of metal. But look here, in brown, you can see this is the key for aluminum, and they're using almost twice as much aluminum as anyone else, and even as though Tesla is into an aluminum steel hybrid body structure, they're still not using near as much aluminum as the folks at BMW. So when you think of that plastic composite vehicle, remember that a biggest portion of its weight is actually in aluminum. And these are what we see as trends moving forward in battery tray. As volumes increase from 30 to 50,000 annually up to 100 and 300,000, so we're going from BMW volumes here to Tesla, expect to see the construction of aluminum battery tray enclosures to move from extrusions and castings to sheet-intense constructions. The sheets are substantially more cost-effective in large volumes, and you can see that these are the vehicles using extrusions here, I-Pace, e-tron, Neo, but they're all relatively low volumes. When we get into higher volumes, you're going to see more and more stamped components in these assemblies. The high specific energy absorption and capacity of aluminum makes an ideal candidate for a protection plate underneath the cells, as in Tesla, where they demonstrated in the Model 3 as 61 series aluminum, very puncture resistant. Integration of liquid cooling strategy with a robust structure for both body integrity and cell protection is a trend for aluminum closures, which you will see more of in the future, we believe, and further advances in high-strength aluminum. And these are the 6,000, the 7,000 series. These alloys, such as the Novelis brands in the 650 and 700 series, they have tensile strengths which are in the 400, 600 megapascal range, and with specific tensile strengths higher than pressure-hardened steel. So there's really some great advancements in aluminum that will allow you to create lightweight structures with little or no steel in them. And we see that as the trend moving forward. Lightweight designs of enclosures that can increase the range more effectively than adding cells. Save weight, extend your range. So I'd like to thank you all for your time today. I've run a little bit over. I wanted to save more time for questions. But please, anytime you are in the Auburn Hills area or visiting Detroit, Michigan, try to make time to visit us at Munro and Associates. Here in Auburn Hills, I'm working out of our Benchmarking Innovation Center, and this is my contact information. You can find me at rgillingham.leaddesign.com. There's my mobile number. Please, I would also invite you all to click on my name on LinkedIn. I'm publishing articles on a regular basis and trying to share the most important elements of our jobs, which are the acquisition and application of the technical knowledge that is just overwhelming so many of us today. I'd like to thank you, Joe. I'm going to turn this back over to you, and hopefully we have some folks that are ready to ask some questions.
Yes, thank you. We do have a couple of questions. I know we have only a couple of minutes left, so hopefully we can go through this pretty quick. Did you see an opportunity back in the i3 to replace those machined parts with additive manufacturing or 3D printed parts? Did we lose you?
Unmute my speaker. Yes, 3D printing is something that is coming into some high volume applications. Recently, I saw an application for a seat belt anchorage in a GM SUV. So that's running in approximately 200,000 units a year. However, the size of 3D printed parts has a large impact on the cycle time. So I do believe that some smaller components may end up being 3D printed. I don't see it for the larger chunks of these systems.
All right. Speaking of the battery packs you went over, are any of them engineered for ease of replacement, like quick changeouts?
Well, they are not exactly what you would call engineered for quick change out. However, the battery system of the BMW and the Chevy Bolt are both more serviceable than the Tesla 3. The Tesla 3 has 4 chunks that you can attend to and service. Contrast that to the Bolt, which has what looks like a library shelf of cells, and they're all side by side. So if you can identify which cell is problematic, that cell can be removed. When you start talking about the Tesla, you have to replace that entire log. So servicing is going to be much more expensive on the Tesla than it would be for either the BMW or the Chevy Bolt.
Got it. I think we have time for one more, and this is a good question, because what we do here at Lyft is we really try to cross-pollinate industries and have applications across multiple industries. Are there recommendations for optimizing the best features of some of these designs into hybrid aircraft application.
Yes, just earlier today we were talking about some of the construction methods and manufacturing methods used. Certainly when you look at the Chevy Bolt composite battery tray cover and the depth of draw, that speaks to some of the geometry that you would see in aerospace, where there are draw ratios, almost in a 1-to-1. And typically, when you talk about sheet metal, you want to have the width of your depression 3 times wider than the depth. In composites, you have much greater flexibility and can almost pull to a 1-to-1 depth. So I do see that in the unique packaging requirements of aircraft, that probably the composite aspects of what you're seeing on that Chevy Bolt are going to be most transferable into the aerospace industry.
Excellent. Well, we have hit the top of the hour. I do want to be respectful of people's times. As a reminder, this webinar will be posted on the lift.technology website. I want to thank Ron. I want to thank Munro and Associates for presenting today. Very good information. I know there's some other questions we couldn't get to, but please reach out to him with his contact information you saw on the screen. And again, visit with Munro, and while you're in the Detroit area, come down and visit Lift. So thank you, Ron. We certainly appreciate that. And for everyone else on the line, please check back for our next liftoff coming up the 3rd Thursday of January. And happy holidays, everybody. Thank you so much.
Thank you, Joe. Have a great day.